Welcome back to the Positron Lab. This is part 3 of our ongoing series with the positron beamline. Today our focus will be benchmarking the positron beam guide or beam line itself. You will see this now in place in the fume hood here, and you will notice that as we look more closely there are alternating red and white wires. I'll come back to that in just a minute. These are also spaced, the coils are they're spaced in intervals of 10 centimeters apiece apart. And then of course they run from our source chamber here with the 10 grams of iodine in the vessel that will be used again as our visual marker, the same as we had in part 2. This will continue to run through and be measured in the flow meter, in which it will then enter a temperature-controlled reaction vessel to maintain adiabatic conditions. Before we run our experiment today, I will again emplace the sodium iodide counters so that we can have coincidence counting, but again our focus will be on the beamline itself. You will notice then that these wires then will run over here to a power supply. Let's take a look at this terminal for just a minute. The wires going into the white terminals are from the direct current beamline, and we will be running between 8 and 12 volts direct current through these. Since the terminal orientation does not matter because it is a bidirectional, we could swap the terminals and make this system bidirectional. But instead, to keep these straight, we are using black leads for our direct current, and then we will be using the red leads for our alternating current, which you will see here represented in the terminal. The importance of this is that in a particle confinement system, we have several options, as we mentioned in part 2. One of those is electromagnetic confinement. This can be obtained by using a quadrupole. It can be used by using a bar arrangement using alternating current. The reason for this, of course, goes back to our discussion yesterday of the beamline and the positron and electron. Positrons are positively charged, hence their name. They're also antimatter, so that if they touch any matter, they will annihilate, releasing 511 keV energy. As such, then, it is one of the ways to keep these confined then is to maintain them in a system of positively charged environment, so like repulses like. We obtain a more efficient clumping, though, if we rapidly alternate the positive and negative poles. In North America, of course, this is going to be a 60 Hertz system, so that these poles are alternating 60 times a second, or 60 cycles per second, whatever terminology you would like to use to describe those. On the other hand, direct current makes a much more ideal electromagnet. So therefore, in this system, we are combining the two. This is a novel arrangement. It is an experimental arrangement, but our hope is to obtain the electromagnetic confining efficiency of alternating current. We're also hoping to obtain the electromagnetic efficiency of direct current. Moreover, and let's return to the beamline itself, you will notice that these coils range from anywhere from 12 turns to 36, or in fact there's a 48 turn coil on the beamline. What is the purpose of this? Well, this is technology that we have borrowed from particle accelerators so that we can obtain not only electromagnetic confinement as the positrons flow through the system in a gas, but we can also accelerate them, speed them up. Of course, acceleration is change in velocity over change in time, and therefore we hope to exploit this principle. To review, we already have 10 grams of iodine in place as our marker, so we're going to begin at this time to heat that system. We will also lower the sash here in just a moment once we place the coincidence counters, and then we will begin to be ready to make a run today experimenting with our flows, our iodine flows, and hence by inference we can also obtain data about our positron flows, as well as to confirm certain things that we want to test with positron transport theory, especially the ways in which it interacts as positronium, orthopositronium, parapositronium, which of those do we have in this system, and to try to find an efficient way to transport those from a source, whether it be a source chamber such as this that we have simply put together for experimental uses, or whether it be a reactor, an accelerator, a cyclotron, any of those. Later, we will be bringing in a neutronic source. We will be using an americium beryllium source of low activity to see that if we can activate some copper-64 and use that to transport. But for now, we're going to focus on the iodine. So therefore, stand by for part 4, in which we will be running the system under electromagnetic confinement, as well as exploiting the accelerator technology that the coil spacing will afford us.